Weird. So let's see here. You got your assignment 2. I know. Don't worry, it's only 2 questions, right? And again, the whole idea is for me to critique your work. So do your absolute best, of course. But this is a chance for me to give feedback before the test. So low stakes, and then get you on track for the test. All right, test 1 is on chapter 4 and 5, so simple interest and compound interest. Right, and so that's on November 5th, I want to say. Right. So just before the long weekend, or I guess the Monday before the long weekend. Oh, did anyone not get their test 1 back yet? If you haven't grabbed it, come grab it. I don't want it. Okay. So, oops, what happened there? Oh, number 2. Do October 31st. Oh, what the? Okay. Took a while. Totally. Like, yes, we should. Like, sold. Charge my pen while we're at it. Okay, so written assignment 2, okay, is due a day after written assignment 1. Fun, right? One thing that I want you to notice, right, is that I ask you to answer the question using the time value money functions on your calculator. I suspect we won't get to those until Monday, okay? But once we cover them, they'll be really easy, right? So you will be able to do question 1A and C, and question 2A and B, but not C, probably until next day, right? So all these compound interest problems, we're gonna do by hand. Yeah.
Question 2A and
A and B, and then not C until probably next day, unless I go through the calculator today. But I don't think I'll have time. So you'll be able to do the majority of the assignment. And then on Monday, I'll show you how to use your calculator. So we're gonna start doing everything by hand for compound interest. And then I'll show you how to use your calculator, and you just plug everything in to your calculator, and it just tells you the answer. Nice, right? So show you how to do it by hand. You have to know how to do it by hand, of course, but you also should know how to use your calculator to do this easy. Okay. Any questions about those? Right, make sure that you do that Moodle assignment that's due at midnight on Sunday. Okay. This should be enough for the pencil, for a bit at least. All right. So you will be able to do number 1, A and I think C. A and C, and number 2, A and B after today. So just as a quick review, we finished chapter 4, right? So we finished chapter 4. Simple interest. Oops. We talked about finding the amounts of payments, right? Finding the amounts of unknown payments, which I think you have another scenario like that on assignment 2, okay, written assignment 2. So written assignment 2 is going to be on compound interest, written assignment 1 is on simple interest. Basically just practicing for the test. Okay. And then we talked about changing interest rates. How do we deal with changing interest rates? In the simple interest scenario, we said, well, we could calculate the amount of interest at each point, add those all up to get our future value, for example, right? Or we can just use the future value formula where the rate and the amount of time changes for each increment. Okay. So then we started, started chapter 5, compound interest. compound interest, the idea stays the same, right? We invest some amount of money and it sits there for some amount of time, right? But the only thing that's changing is that the interest rate is now being compounded at some frequency, right? Where we take the amount of interest that we've earned, compound it with the principal, and then we earn interest on that and the principal, right? And then we keep going until the next compounding period, compound, right? So it just kind of snowballs, right? And so the difference is, instead of time, now we're interested in the number of compoundings, right? So for compound interest, problems, we replace, I'll put air quotes around replace, right? We're still going to have time, but we need to know the number of compoundings, right? Not time anymore. So we replace time, t, with the number of compoundings lowercase n. Right? So on our timeline, on our arrow, we used to put the time, right? But now we put the number of compoundings instead. And remember, we said, and we're going to calculate as t times f, right? Where f is the compounding frequency. And we went through a list of frequencies we need to know. The trickiest are probably bi-weekly, 26 times per year, right? Weekly, 52 times per year, monthly, 12 times per year, right? Annually, once per year, semi-annually, twice per year, right? So we made a list of all those that we need to know and have in our back pocket. Okay. And we also, I'll put air quotes, physical quotes on here, but replace. We're not replacing anything, but in our calculations, we don't use R anymore. R we call the nominal rate or the annual interest rate, right? That's not the one we're going to use anymore. We have to use our periodic interest rate, I. Okay? So we replace the nominal interest rate R with the periodic interest rate I. And on your formula sheet, right, you have I equals R over F. So you take your rate, divide it by how many compoundings per year you have, and then that's how your periodic interest rate for each period. Okay. And then we said, well, our future value for compound interest, right, is going to be the present value times 1 plus I to the power of n. And we also said we developed the formula for the present value. It wasn't that hard. It's the future value divided by 1 plus I to the power of n. So same idea as simple interest, right? Now we just have this added element of having to calculate the number of compoundings, but also the periodic interest rate. And then we can just go ahead and use the new compound interest formulas instead of simple interest formulas, right? But the ideas all stay the same. Okay. Any questions before we start some new stuff? Cool.
So the replacing is just for the compound interest, for the simple interest to stay the same.
Yeah, so I mean replace from simple interest, right? So what we have learned already, we're replacing, because we used to have to find time for the length of the arrow. right? And we have to use the rate, which is just given, right? Now we have to find the periodic interest rate and find the number of compoundings. That's all. Okay. So 5.3 is on calculating the periodic interest rate I Do you figure it out, Braden?
Yep.
The assignments? Yeah, I know. I'm not clever enough to figure out my own. Of course they're stolen from the textbook. Guys.
I only have the first book though, so I don't know the answers.
I have the answer.
But they're in the back.
Well, just
Oh,
the answer.
yeah. That's okay. Everyone runs to the bookstore. It doesn't quite work like that. Okay. And the number of compounding periods n. Right. So just like before, we go through, we take this future value formula, and now we dissect it, and we've solved for the present value. Now we have to move through, and we have to solve for I, and then we're going to solve for n. Right. Look at examples. If we have to solve for I, and if we have to solve for n, what do we do? Okay. So solving for I, let's start there. From our formula, and you don't need to know how to do this necessarily. It's on your formula sheet. You know what we're working towards, right? I is the nth root of FV over PV all minus 1. That's on your formula sheet. I'm just going to show you how we got there. Because like I said before, I actually prefer to only be given one formula, and then I have to rework it for whatever I want to solve for. But that's just me. Others like the same formula reworked a bunch of times over, just like on your formula sheet. Okay, so we want to solve for I. So we first have to shake the PV, so we're going to divide both sides by PV. So the future value over PV is 1 plus I to the n. How do we ditch that power of n? We have to take the nth root of both sides. Right? So now we take the nth root. We show that by putting the n in the little hook, right? Nth root of FV over PV is just 1 plus I. Right? Taking the nth root of something to the power of n, just they dissolve. That was the whole goal, right? So now we have 1 plus I. So now solving for I just subtract 1 from both sides, and I'm done. So then I is going to be the nth root of FV over PV all minus 1. Cool. I remember is the periodic interest rate, right? Usually I'll want to know what the nominal interest rate is, right? So usually we will want to know the nominal rate, which means we have to solve for R, right? So then once we've solved for I, so step 1, solve for I, right? And step 2, use I equals R over F to solve for R. Right? So it kind of has that added element of calculation. So let's do an example, and I think I have to steal it back from here. We're going to do example 178. Oops. $15,000 was invested for 13 years until it reached a value of $30,000. If interest is compounded monthly, what was the nominal rate of interest? All right, so here I'm asking, what was the nominal rate to make something go from 15,000 to 30,000 over a time period of 13 years? Right? So we don't need a timeline. I think it's going to be a good idea to make one, just to visualize what's going on. Okay. And so we have some amount, let's say today, and then 13 years later. Right. Those are the only time points that we're talking about. Okay. And we know that I invested 15,000 today, and it's going to grow to 30,000. Okay. So in terms of our present value, future value, right, our present value is 15,000 because it's on the left-hand side of the arrow. Future value is the 30,000 because it's on the right-hand side of the arrow. Okay. And then we've got compound interest, right? So let's just make a note here that R is what we want to know, and F is the compounding frequency. We're compounding monthly, right? So 12 times per year. We can still figure out N for this arrow, right? N is time times the frequency. The time in years is 13 times 12. Yeah, 156. So what we have to do, right, is we first have to solve for I, and then we can solve for R. Right, so this is our done timeline. It's pretty simple, but solve for I. We have our formula for I, right? And we just developed it up here. So I is the nth root of the future value over the present value, all minus 1. Our future value is 30,000. And our present value is 15,000. And we want to take the nth root, so the 156th root. And then all minus 1. That's going to make a big difference. You have to subtract the 1. Don't forget about it. Okay. How are we going to do? Well, we can simplify 30,000 over 15,000. So this becomes the 156th the root of 2 minus 1. How are you going to do the 156th root on your calculator? You're going to so on calculator, right, you're going to do 2 to the power of 1 over 156. Right, so on your screen, you're going to have 2, and then you're going to do the y to the x button. And then I put brackets around because I have 1 over 156, right? I don't want to leave it to chance. I want to leave that 1 over 156 as one value. So I put brackets around, and then 1 divided by 156, and then n bracket, and then equals. Okay. So I've got 2 to the power of bracket 1 divided by 156 n bracket equals. So I get equals 1.004453137. Right. So the 156th root of 2 is 1.004453137. So I'll just write that in here, 1.004453137 minus 1. Right. If you forget to do the minus 1 and you just left your I, your periodic interest rate, as 1.00, that's like 100% a month. That's insane, right? So your rates are always going to be very small, right? Small, nice decimals. Okay. So then minus 1, of course, we get 0.004453137. Keeping all your decimal places, that's important. Okay. So now you can use your fancy store button if you want. Make sure you don't lose it. All right, store it in 1. Why not? Just in case. So this is I. All right. So we found I. Step 2 is going to be solve for R. Because the whole goal was to find R, but in order to do that, we first have to find I, and then we can find R. Okay. Solving for R, we have I equals R over F. Okay. So I is 0.004453137 is R, which we're trying to find, over F, which was 12, right? Yeah. So multiplying both sides by 12, right? I've still got it on my screen. I didn't really need to store it, but I just wanted to show you again. Times 12, we have a nominal rate of 0.053437644. Therefore, the nominal rate is approximately 5.34%. Do 2 or 3 decimal places, yeah. Did I do time? I have time is 13. Did I use it though? 13 times 12, 156. Yeah, so time is 13. But I is R over F. Yeah. So that's the one you'll want to use. I'll clean it up. How about that? Yeah, but that's going to make a big difference, right? Cool. We did it. So 2-step process now, right? If you have to find R. Before we were just able to solve for R and then just solve the equation for it. Now we have to always find I first, and then we can find R. Right? So we're going to have a same situation or the same type of situation if we want to solve for time, right? Because we'll first have to find the number of compoundings, and then we can solve for time, right? So just like how we take the time and calculate the number of compoundings, and we take the rate and we calculate I, the periodic interest rate, now to solve for rate or time, we have to work them back. Yeah. So solving for n. Any questions about that example though? Huh? Oh, new question. So here's how we're going to solve for n. We have our future value is our present value times 1 plus I to the power of n. Oh shoot, we've got this n in the power and we want to solve for it. Something about logs, right? It was a while ago that we went through the log laws. Okay. But we're going to take the log of both sides, and that's going to bring that n down in front. Right? But first we have to divide both sides by PV. So we get the future value over PV is 1 plus I to the power of n. The goal is to solve for n. So then we can take the log, the natural log of both sides, the future value over the present value. It's the log of 1 plus I to the n. Which just becomes the n times the log of 1 plus I, right? By log rules. Right, we talked about that. So now we have the log of the future value over the present value is n times the log of 1 plus I. So solving for n now, we can divide both sides by the log of 1 plus I. So we have n is the log of the future value over the present value over the log of 1 plus I, which you can confirm is exactly what's on your formula sheet. Just showing you where it came from. And you can solve for it too. Any questions about that one? Okay, so just like we said up here, right? Instead of solving for n, we usually want to solve for time. Right? So we usually want to solve for time t. So step 1 is going to be solve for n. Step 2 is going to be use n is time times the frequency to solve for t. Just have to take that extra step further. So let's do example 179. In order to save for college, you want to invest $10,000 and have it grow to $15,000. That sounds great. It's not, as you all know. But anyways, if the rate of interest is 8% compounded semi-annually, how long will it take for this to occur? Right, so how long is it going to take? We need to know time, right? We don't talk in the number of compoundings, n, right? We talk in t, time. Right? And so the first thing we have to do, right, is solve for n, and then we can solve for t. Okay? So let's map this out. It's going to be a nice, simple timeline, so why not? Right, so here we are today. Oops. And here's future you. Okay. And we're told we want to invest $10,000. Remember, the dollar amounts just go below the ticks. And then our arrow to our future amount of $15,000. So my present value is 10,000, my future value is 15,000. Right. And I'm told that the rate is 0.08 and the frequency is semi-annually. So the frequency is twice per year, right? Compounded twice per year. I'm going to indicate that I don't know n, right? And I'm going to calculate I equals R over F, which is 0.08 divided by 2, 0.04. So now I have to remember to calculate I because that's the one I need in my calculations. Okay, so first thing we're going to do is solve for n. We can use our formula. N is the log of the future value over the present value over the log of 1 plus I. So far, so good. The log of the future value is 15,000 divided by the present value, which is 10,000, over the log of 1 plus I, which is 0.04. So I'm going to simplify in what's inside the log. Right. 15,000 divided by 10,000. The log of 1.5 over the log of 1.04. Remember to take the log of something. You have what you want to take the log of on the screen, and then you hit the LN button. It's above the store button. Right. So here. $1.5 and then LN. So I get this kind of big decimal, 0.405465108. I'm going to store this just in case I lose it. I'll store it in 1. Divided by 104, 1.04, and the log of that, 0.039220713. I'll store this in 2, just so I have it. You're better off storing than not storing stuff, even if you don't use it. So now I want to recall 1 divided by recall 2. I get 10.33803507. And that's our N. So I stored 0.405 in 1, and then I stored 0.0392 in 2. And then I did recall 1 over recall 2.
So this divide by that.
Yeah. Yeah, make sure it works out, but this is what I have in my notes too, so it should be okay. Is anyone getting the same as I'm? Yeah, cool. Good. So we need 10.33803,507 compoundings. That's not gonna happen, right? We can't do a partial compounding. We've got that scenario. We've seen that before, right? Where we can't make a partial payment, or we can't have a partial compounding. So for the number of compounds, we always have to round up, right? So that means that we're gonna have a little bit more than 15,000 in the end, but I think we'll survive, right? Because we have to take it that 1 extra compounding. So we can't have a fraction of a compounding so we always round N up to the nearest whole number. So we have to use N equals 11. We need 11 compoundings to make this happen, right? Because what's going to happen, right, thinking about your timeline, if you only went to 10 compoundings, right, it's saying the full length of this arrow is 10.3 whatever, right? So if you only went to 10, you wouldn't quite make it all the way, right? So that's why you have to go to 11, which is going to take it a little bit further, right? Which means you're going to have a little bit more than 15,000, but that's the price of doing business, I guess. Okay. So we use N is 11 for our calculations. Now our second step is to take N to solve for T. So now solve for T. N, remember, is time times the frequency. If N must be 11, we're trying to solve T, and the frequency, I think, was 2, right? Yeah, nice. So then solving for T, we get 11 over 2. $5.5 years. Therefore, it will take 5.5 years for 10,000 to grow to 15,000, right? At that specific interest rate. Can't even remember, 8% compounded semi-annually. At 8% compounded semi-annually. Nice. Any questions about that one? No? Cool. We're rocking and rolling here. Okay. Well, that's the end of that one. Doubling time. I think you guys have seen this probably in some of your other courses, right? So the doubling time is just an approximation of how long is it going to take for some investment to just double, right? Doesn't matter what you start with or what you want to end with, right? Regardless of the amount that you start with, how long is it going to take for it to double? The rule of 72. Does that ring a bell? Nice. Okay, so the doubling time is you just take 72 divided by the percentage. And that's it. Okay, so doubling time. The time it will take any investment to double in value can be approximated by the rule of 72. This says rule. Okay. So which says that the doubling time in years is roughly equal to 72 divided by the percent annual rate. This is one of those rare times where we don't convert R to a decimal. We leave it as the 8% in the previous question, for example. All right, so it'd be 72 divided by 8. Okay. So what we have is we have 72 divided by the rate as a percentage. So it's basically the same as what we just did by example 181. Why not? An investment of $15,000 needs to double, right? The rate of the rule of 72 doesn't actually care what the amount is, right? All it's going to tell you is how long it's going to take something to double at this rate. So it also works for things like population growth. If you know the rate of growth, right, you can do 72 divided by the rate, get a rough approximation of how long it's going to take this population to double, bacteria to double, that kind of thing. Yeah. Just, yeah, there's math logic in there, but who cares about that? I think the textbook goes through and shows you why, but yeah. Just a fun 72. Okay. So then we have our doubling time is roughly, so at a rate of 8% per year, that's the only thing we need, really, to calculate an approximate doubling time. At a rate of 8% per year, roughly how long will it take? So then we've got 72 divided by 8, leaving that 8 as a whole number. So then we have 72 divided by 8. It's going to take roughly 9 years. So double. So regardless of the amount that we're talking about, right, for it to double, 72 divided by the rate. That's good, kind of quick and easy, right? How long is it going to take? So say you're at the bank, right? They offer you a rate, and then you think, oh, okay, well, how long is it going to take for that to double? All right, you don't have to do any math. You can just do 72 divided by the rate that they're giving you, and then you can decide if that doubling time is good or bad, right? It's up to you.
I hope there's a lot of questions about that.
Yeah, well, how about I'll throw at least one on there. Not, well, I mean, technically you could use,
I mean, you can see what
yeah, I mean, you could make it a bigger problem than it is, right? You could just say, okay, my present value is 15,000. It has to double, making the future value 30,000, right? And then, but if I'm asking how long is it going to take for it to double, right? I don't even need to give you the 15,000, right? So the question could just be, without the first part, right? It could just be at a rate of 8% per year, roughly how long will it take for an investment to double, right? And that's when you use the 72 over 8. Guaranteed 1 on the test. How about that?
use the negative. You can use it to find out how long it takes to have.
Has to do with the logs, the natural logs. Would it behave the same way? The log of 0.5. Yeah, be roughly negative. I'm getting negative 69, but yeah. Anyways, doesn't matter. Rule of 72, folks. I guess you see it in other classes later, which kind of, I thought I was blowing people's minds last term, but I wasn't. Like, yeah, we've seen it already. Fine. So, that's just a quick little fun one. Any questions before we keep going? No questions. All right. 5.4, oops, hole punch through it. Equivalent payments and payment streams sounds like huge timelines to me. And that's what we're building up towards, right? With establishing formulas for all these things, the future value, the present value, I and N, right? The whole goal is to be able to tackle a huge timeline like what we're about to do. Okay. So equivalent payments and payment streams. We'll start things off with example 185. Oof. It's a biggie, as we kind of knew if it's going to be a timeline question. Let's read the question first, right? And then we know the next step is to identify all the different time points that we need to plot on our graph, right? Potentially the hardest part in dealing with these timelines, right, is figuring out what dates we need to put on there. So I'll have to read off here. Doug's original intention was to settle a financial obligation with 2 payments. The first payment of $1,500 was due 1 year ago. Okay. And the second payment of $2,500 is due 3 years from now. Okay, and a little lofty repayment schedule. Doug missed the first payment. This is always going to be the case. Oh, you missed the first payment. Now you have to restructure the loan. What happens then? Right? And so Doug missed the first payment and now proposes 3 payments that will be economically equivalent to the 2 originally equivalent scheduled payments. Ugh. The replacement payments are $1,000 today, okay, a second payment in 1.5 years, and a third payment twice as large as the second in 3 years. What should the second and third payments be if money can earn 8% compounded semi-annually? If you've had a peek through assignment 2 already, you'll notice that this is very similar to question 2. Again, all right, very similar. I'd say question 2 on the assignment is a little bit easier than this one, but better that than the other way around. Okay, so we had our, let's map out the original payment schedule and the new payment schedule separately because it's hard to keep track of all these things, right? So we'll start with our original, the original payment schedule, and then I'll take these and make a timeline. Okay. Did you get assignment? Yeah. Oh, 2 though, not 1. Yeah. So the original payment schedule, right? So he was going to make 2 payments. So from today, he had 1 a year ago that he missed, and then 3 years from now. All right, so the original payment schedule would look something like this. So today, and 1 year ago, and 3 years from now. Just kind of untangling this mess before I make my timeline. The new payment schedule, oh, I'll put the amounts on here just because. The first payment of $1,500 was due 1 year ago, and the second payment of $2,500 is due 3 years from now. So this was the original payment schedule. So now the new payment schedule is going to be, the replacement payments are $1,000 today, a second payment in 1.5 years, and then a third payment twice as large as the second in 3 years. Right. So now we've got, so from today, he's going to make a payment today, a payment in 1.5 years, and the last payment in 3 years. Okay. I can put the amounts on here just because the replacement payments are going to be $1,000 today, and a second payment in 1.5 years, and a third payment twice as large as the second. So we don't know what the second payment amount is. So how we tackle that is we just use X, because then the second, or the third payment, I guess, is twice as large as the second, right? So we're just going to use 2X. Nice. Okay. So now we can put these all together on the timeline, right? We want to. I just find it's helpful to map out the original one and then map out the new one and just kind of see what's going on before I go ahead and make my timeline. Okay. So now I know that, okay, well, my timeline, I'm going to start at a year ago and go to 3 years from now. you technically only need this last one that I'm doing. But I did the first two just to map out what's going on, kind of get them all straight in my head. And then I can make my but I'll just highlight that this is the timeline. So this is the one that you need. And if you can start from here, that's great. I definitely couldn't. So, okay. We need to know what X is, right? So it doesn't matter what we use as the focal date. The focal date, remember, is where we're going to draw all our payments to, right? And so we know that we're going to have X at 1.5 years. So I don't know, let's use 1.5 years as the focal date. Let's mix things up. You can try any focal date and you'll find that you find the same thing, right? The same X. Okay. But just to mix things up, let's use 1.5 years as our focal date. Okay. Let's use 1.5 years as our focal date. Oh. All right. There was no reason for doing that except that I have an X at 1.5 years, which means I don't have to use X as my future value or present value. I can just have X there. I still have to deal with 2X, right? Discounting the 2X, but it's just less X math. Okay. That's the only reason. Okay. Let's map out our original payments then and figure out what the original payments plan is worth at 1.5 years. So once you've decided on your focal date, right? And I said that on your assignment 2 is I said, show the complete timeline for question 2, clearly indicating the date you will use as the focal date, right? So you can use whatever you want, right? But you have to tell me which one you're going to use as the focal date. Okay? So if we're using 1.5 years as our focal date, right, all our payments have to be drawn to 1.5 years. So in our original payment plan, we were supposed to pay $1,500 here. In 1.5 years from now, right, that's going to be worth some future value. And that's the first thing we're going to calculate. Okay. So how I want you to think about it, right, is we essentially have to re-borrow the 1,500 for a year plus 1.5 years. Okay. But let's get the amounts on here first. And then we were supposed to pay 2,500 at 3 years. So we had 2,500 here. That's getting pulled back to some present value. And that's the second thing we'll calculate. So if we add these up, so now I've started using the subscripts as the order of my calculations. So you can do future value and the present value of the original loan in any order, right? But you have to find the total that they're worth at 1.5 years before you can go ahead and figure out the second payment plan. Okay? So the total here is the total original value at 1.5 years. So we want to find a payment plan that has that same total value at 1.5 years. Okay. So then we have our new payment plan where we're going to pay $1,000 today. X at 1.5 years and 2X. Actually, I'll put these down below here. 1,000 today, X at 1.5 years, and 2X at 3 years. Got too messy. Okay. So my focal date stays the same. So I'm going to draw this $1,000 to some future value 3. Calculating that third. And then this 2X, oops. Oh, come on. Becomes some present value 4. So X plus future value 3 plus present value 4 has to equal the total original value at 1.5 years. Right. Must equal the total original value at 1.5 years. So like I said, it doesn't matter what you use as your focal point or focal date, right? As long as you are drawing all your payments to the same date, doesn't matter where you do it. Okay? You just want to pick one with the least amount of work, usually. We like to do that. Okay? So we need to finish up our timeline. We have to know n for each of these arrows. Right? So n for this first one is time times the frequency. The time is, so the length of this arrow in time is 1 year plus 1.5 years, so 2.5. And F, what was the frequency? If money can earn 8%, so the rate is 8%. And the frequency is semi-annually. And we want to know what the second and the third payments are. That's our overall goal. Okay. So we know that the frequency is 2. So I have 2.5 times 2 is 5. For between 1.5 years and 3 years, the length of the arrow is 1.5, right? So n is 1.5 times 2. 3 compoundings. And again, n is from today to 1.5 years from now is 1.5 times 2, which is 3 again. And same thing here, n is 1.5 times 2, which is 3. We also, right, the rate for these, thank goodness, doesn't change. That's a reasonable twist. So the original loans, they had a rate of 4%, and now the new loans have a rate of 9%, something like that. Right, we don't have to deal with that for this question, but it's something that we could have to deal with, right? So now we have to find I is R over F. R is 0.08 over the frequency, which is 2. So we have I is 0.04. Okay. this here is your complete timeline. I'm trying to squeeze it all in there because we have to have all our time ticks indicate our focal date now, right? That's going to be important. Have all our arrows, all our calculations. This is just a map of all our calculations that we have to do, and we have to squeeze in I. Maybe I'll move it. There. Now I can show you the complete timeline on one screen. So all of this has to be on there. So now we get to work. All right, so now we're going to find we'll start with future value 1. Future value 1, oops, is the present value times 1 plus I to the n. The future value 1 has a present value of 1,500 times 1 plus I, which is 0.04, to the power of n, which was 5 for this one. So we have 1.04 to the power of 5. I'll just jot it down. 1,500 times 1.216652902 times 1,500. We have 1824.98, rounding to 2 decimal places. All right, great. Let's find our present value 2. The future value was 2,500. So now find present value 2. Present value 2, we can just use our formula on our formula sheet, which is the future value over 1 plus I to the n. The future value for this little guy was 2,500 over 1 plus 0.04 to the n, which was 3. You can see how important it is to not use R, right, where you should be using I. Right? The difference between 0.08 and 0.04 is going to make a big difference. So 1.04 to the power of 3, 2,500 over 1.124864. 2,500 divided by that, 2222.49, rounding to 2 decimal places right away. So you keep all your decimal places until the end, then you can round to 2 decimal places. Yeah. Oh yeah, sorry. Is that good or? Okay. So now we know the total original value at 1.5 years, right? It's going to be the 1824.98 plus 2222.49, right? So our new payment schedule has to be worth that exact same amount. Okay. Scroll a little bit. So the total original value at 1.5 years is going to be future value 1 plus present value 2, which was the 1824.98 plus 2222.49. 498 plus 2222.49. $4,047.47. So we had to figure out the original payment, right? Because we need to know the total of the new payment to figure out that unknown payment amount, or those unknown payment amounts. So now we can get to work and we can find future value 3. Now find future value 3. Future value 3 is the present value times 1 plus I to the n. Present value of future value 3 was $1,000. Times 1 plus 0.04 to the power of n, which pretty sure was 3 for all of these guys. So 1.04 to the power of 3, I have 1,000 times 1.124864 times 1,000. 1,124.86. And now we're going to have to find present value 4. Present value 4 has a future value of 2x. We looked at how we deal with this in simple interest last day, right? But it's the exact same scenario as in compound interest. So we use our 2x as our future value, right? And we just do our calculations. So present value 4 is the future value over 1 plus I to the n. Future value is 2x over 1 plus 0.04 to the power of 3. One 1.04 to the power of 3 is still 2x over 1.124864. Remember our 1 over x trick? To kind of bring it to the same level, right? You're going to rewrite this as 1 over 1.124864 times 2 and then times x. So just as a little side note, right, on your calculator, you're going to rewrite this as 1 over 1.124864 times 2x, right? Use the 1 over x button. So if you have 1.124864 on your screen, you can hit the 1 over x button. I'll just show you what I get here. I get 0.888996359 times 2x. I can multiply by 2, right, to just get one coefficient. So times that by 2, I get 1.77799217x. This is kind of a long, nasty one, right? So I'm going to store this in 1. Is everyone getting the same thing? Yeah. All right. So now the total value of new payments must be the same as the total value of the original payments. Oh, come on. Right. The total value of the original payments was $4,047.47. So $4,047.47 must be the same as, and looking at our timeline here, as X plus future value 3 plus present value 4. Woo, woo, woo. X plus future value 3 plus present value 4. Don't forget that X, right? We only used 1.5 years as the focal date because we had that X there, right? So we wouldn't have to have 2 decimals in front of X. Just matter where you pull it to though. But as long as you don't forget about X, which means we have X plus future value 3 was 1124.86 plus present value 4, which is that huge 1.7779927717X. Luckily, I've stored that. Because now I'm going to collect like terms, right? I've got X plus 1.77X. So I can just add those up. So I get 1124.86. That one doesn't have an X, so it just stays on its own. Plus 2.7779927717X. Collecting like terms. This whole time, this all equals 40, 47, 47. Trying to solve for X, right? I can subtract 1124.86 from both sides. So I get 40, 47, 47 minus 1124.86 is 2.7779927717X. 4047.47 minus 1124.86, I get $2,922.61. Is 2.7779927717X. Finally, we can shake out that X, right? I can divide both sides by, I'm going to do bracket, recall 1 plus 1, end bracket. 2922.61 divided by 2.7779927717. I get an X of 1052.06. Oof, phew. Yikes. We're almost done. What? We thought we were done. No. We want to know what the second and the third payments are. The third payment is twice as much as the second payment. We're so close we can taste it. The first payment must be 1052.06. So the second payment is 2x, which is 2 times 1052.06. 2104.12. Now we're done. Celebrate. Nice. Huh? Yeah. It's just to show that it's the end of the question. The end of an era. Does the squiggly mean celebrate? I wish. Maybe it does. Maybe it should start meaning celebrate. Oh, you think we're done, huh? Yeah, me too. My finger's tired. Unless you want me to show you how to use the calculator to do all this stuff so you don't have to do it by hand. How about that? Let's do it.
But we need to show the detail in the test.
You can use your calculator on the test if you want. And it's worth the same amount of marks. What? Sold. So you guys can stick around for another little bit. Let's do it. Using our calculator. For compound interest problems. My pen's dying. Yeah. No, it's a real experience. Yeah, it gives you the whole gamut. Running out of ink when you have to hit it a little bit. Okay, so while it's charging, we can have a look at our functions. Okay, so the time value of money functions on your calculator are these white buttons and a little bit beyond on your calculator. Okay, this is what you paid money for, ironically. Okay, so just listing them, right? You have n. That's where you're going to put the number of compoundings, right? So you still have to find the number of compoundings, but that's probably not that hard, right? The interest per year, you're going to put the original rate, right? So just your R as a percentage, right? So if it's 8%, you just put in 8. Right? I'll show you how to put them in a bit here while my pen's loading. Present value, you're just going to put the present value. And then you've got the payment. We're not dealing with payments for now, so you just put in 0. And then you've got your future value. One little thing that it needs is the future value and the present value have to have opposite signs. So one's going to be negative, one's going to be positive. Later on, we'll adopt the if money is leaving your hands, it's negative. If you're receiving money, it's going to be positive, right? So if you're depositing a present value into the bank, it's leaving your hands, so then you would do negative, right? For these problems, it doesn't matter which one's positive, which one's negative, as long as one of them is positive and negative, right? So it's going to give you, oh, come on. So it's going to give you a negative or a positive answer. I don't know why it does this. It's not listening. Yeah, like you guys, right? Hey, I wrote just as much as you guys did. But I get to talk at the same time, so it's a little different. Well, it's not working. So it won't let me stop and start it. All right. I guess I'll show you the calculator next day. Yeah. They're just on Moodle, and can I show you? Hopefully it has autocomplete. I'll show you. Because you mean the actual notes, not the videos? Right?
It doesn't really matter to me. I mean,
Okay. Try to take you there. It's a little slow. I'll stop this.